to Biostat Squid. This is the final part of a 4-video series on the differences between UMAP, t-SNE and PCA. If you haven't watched my previous videos yet, check them out for clear explanations on PCA, t-SNE and UMAP. In this video, we'll dive right into the similarities and differences between them. So if you're ready, let's dive in. PCA, t-SNE and UMAP are all popular techniques for dimensionality reduction, but they differ significantly in how they work and what they are best used for. So what are the differences between them? When should we use one or the other? We'll compare the algorithms across 4 main areas: the algorithms themselves, the output, performance characteristics, and finally applications. When should we use one or the other? Let's start by comparing the algorithms between PCA, t-SNE and UMAP. Mathematically, we already know that they have very different approaches to reduce the dimensions of our dataset. To start us off, PCA is linear, whereas t-SNE and UMAP are non-linear methods. What does that mean? In essence, linear relationships mean simple, straight-line relationships where things change at a constant rate. For example, if the expression of gene X is associated with half the expression of gene Y. Nonlinear methods mean more complex, curved, or flexible relationships where things can change in a variable way. So the expression of gene X and gene Y might vary in relation to one another, and high X is not always associated with high Y, and vice versa. When working with data, linear methods like PCA are useful when the data's underlying patterns follow straight-line relationships, while nonlinear methods like t-SNE and UMAP are better for capturing more complex, curved or intricate patterns in the data. In the case of gene expression, we know that the relationship between the expression of most genes is not linear, meaning a change in the expression of one gene does not mean a constant change in the expression of another gene. So that tells you a bit more about how PCA works versus t-SNE and UMAP. But the key difference here is what these methods are aiming for when trying to reduce the number of dimensions from high to low. Obviously, when you're reducing the number of dimensions, you're going to lose some information. So each of the methods uses a different strategy to preserve the most information they can. In other words, each method aims to preserve certain types of structure in the data. PCA preserves overall variance of the data, t-SNE preserves local neighborhood relationships, and UMAP tries to preserve both local and global structure. Nice! So obviously with different methods come different outputs. t-SNE and UMAP are much more similar to each other. We get a 2D or 3D projection, meaning 2 or 3 coordinates for each cell which we can plot. PCA is a bit different since we are in a way getting a new dataset, but instead of genes we have principal components. Remember, sometimes 2 or 3 PCs are enough to explain most variability in the dataset, but more often than not, we need many principal components to capture enough variability in our dataset. So what about performance? PCA and UMAP are great for large-scale datasets. t-SNE is very computationally expensive and slower than UMAP, so it's not the best option if you have a large dataset. In terms of reproducibility, PCA is highly reproducible, meaning you will always get the same results. But t-SNE and UMAP are non-deterministic algorithms, or if you'd like a fancier word, they are stochastic, meaning that if you rerun them on the same dataset with the same parameters, you might get slightly different results each time. This is because both algorithms involve elements of randomness in their optimization process. So if you're using these methods in your analysis, don't forget to set a random seed, which ensures that the algorithm's random processes are controlled and you get the same results each time you run the code. We should also mention that the resulting 2D projection of both UMAP and t-SNE can be fine-tuned with the hyperparameters, as we discussed in previous videos. Since the choice of hyperparameters is so important, it can be very useful to run the projection multiple times with various hyperparameters. There's a great webpage to compare t-SNE and UMAP projections and play with hyperparameters. I'll leave the link in the description below. So, how easy is to interpret the results of these algorithms? PCA is very easy, as we already know. PC1 holds the most variance, so clusters separated in the x-axis are more different from each other than clusters separated in the y-axis by the same distance. We can also have a look at the principal component loadings to see what genes contribute the most to what principal component. UMAP and t-SNE, on the other hand, are a bit trickier. First, you should know that in UMAP and t-SNE, the cluster sizes relative to each other don't mean anything. But most importantly, the distances between clusters do not mean anything. This is because when UMAP is constructing the high-dimensional graph, it uses local distances between cells. So even when we're preserving more of the global structure with UMAP than with t-SNE, it does not mean that this pink cluster is twice as related to the blue cluster than to the orange one. To sum up, in a UMAP plot, relations between clusters are potentially more meaningful than in t-SNE, but they're not directly interpretable like in a PCA plot. Okay, so hopefully this gave you a better overview of the differences between the three methods. Now one question remains: when to use each method? I'll give you a few guidelines, but these are not strict rules and you should always decide based on the data and your goal. So PCA is ideal for datasets where the relationships are mainly linear and you want to retain the most important features. It is commonly used for data preprocessing, for example, noise reduction, feature selection in machine learning, or when working with high-dimensional datasets where you need to keep the overall variance. t-SNE and UMAP are very similar, but because UMAP is faster and less computationally demanding than t-SNE, it's often the algorithm of choice. So t-SNE is great for visualizing small to medium-sized datasets and exploring local relationships or clusters. It's used more when you want to uncover fine-grained structures, like identifying close relationships between cells. Remember, t-SNE focuses on local differences. That is why t-SNE is often used in exploratory data analysis or to visualize the results of complex models like deep learning. Finally, UMAP works well for both large and small datasets, especially when you want a good balance between preserving local and global structure. It is excellent for exploratory analysis and visualizations where you want a deeper understanding of the overall organization of the data, and it is especially recommended for large datasets. One last thing before we wrap up. These methods are not exclusive. You can actually combine them. If we go back to our original example, our single-cell RNA-seq dataset, we can use a combination of these methods to visualize our dataset. For example, we might use PCA to reduce the 10,000 genes to 50 or 100 principal components, and this reduces noise in the data, selecting the most informative features or genes by summarizing them into a few dozen principal components. That way, it is easier to identify underlying patterns, like immune cells versus not, or dividing cells versus not. Then, after PCA, we can apply UMAP on the first 50 principal components to get a 2D projection of our cells, so we can visualize the main clusters of cells based on their gene expression profiles. Nice, you made it to the end. You can find a summary table comparing all three dimensionality reduction methods at biostatsquid.com, and if you'd like a more mathsy explanation of the methods, check out the links in the description. Hope you liked this video. Remember to subscribe if you don't want to miss any more videos from me. Have a squid-tastic day and see you in the next one.